Pleasure to be here and talk to you. It's a variety of thoughts about extreme events and the importance of them in understanding water quality. It is that extreme events are natural experiments, and there is a great deal we can learn about water quality by sampling extreme events. Samples taken during floods in particular are critical to estimating fluxes or loads, and continuous monitoring can help. And I think continuous monitoring is something that's really coming on and is going to be very valuable. But where we're interested in control of the downstream flux of something like a nutrient to a receiving water body, we're critically interested in fluxes, and so much of what moves in the system is happening during high flow events. And getting a handle on that is absolutely crucial. Related to that is the idea that trends in average concentration and trends in average flux can tell very different stories. And just because we have a trend in one doesn't necessarily mean we have a similar sort of trend in the other. And that, again, is why sampling of high flow events can be so important. Low or high flow conditions can have a lasting impact on water quality. So the effect carries over because of the carryover of contaminants, particularly in the soil and shallow groundwater system. And we'll take an example of that. And then finally, I'm just going to very briefly talk about the whole issue of climate change, greenhouse forcing, and hydrologic extremes, and maybe a little bit different way of looking at it than what I see among many of my colleagues. I'm going to start with an example from the Susquehanna River Basin, the largest single tributary of Chesapeake Bay, where nutrients are a very key issue. You see the outline here of the Susquehanna watershed and the location that we're monitoring it, which happens to be at a dam at the downstream end of that system. So this is a satellite photo from a tropical storm Lee, which came through the watershed and was about a 20-year recurrence interval event. And what you see is the plume of sediment extending about 150 kilometers down the Chesapeake Bay, carrying sediment and the attached phosphorus and nitrogen. Some of that coming out of storage in the reservoir, some of it coming from the watershed. We're moving. Now we're moving. I don't know why. Okay, this is the complete data set of the USGS total phosphorus data that's been collected over more than 30-year period at this particular site. And one of the things that's pretty striking about it is that most of the data is below about 0.1 milligrams per liter. A few samples are in the 0.4 milligrams per liter. But then in the last decade, we've seen several examples that are near 1 or above 1, and even one value that's up around 2.5. And we know that some of those are associated with some very high flow events. And so the question that is raised is, what's happening here? Did we not observe high concentrations were we not measuring at high discharges before the last few years, and that's why we don't see any high values? Or has the behavior of the system at high discharges changed over time? And that's where we need to dig into the data set and try to understand what's going on. This is an illustration from a USGS report that I published dealing with this particular event and what it can tell us about the evolution of conditions in the Susquehanna River watershed. So on the x-axis is discharge in thousands of cubic feet per second, just showing you the higher discharges. There are many, many observations below these, but these are the higher discharges. And the discharges that were observed, in some of those that you saw on the last slide are the ones to the very far right and in red. The ones in red are observations that were collected between January 1 of 2000 and October 4th of 2011. Those are the red dots. The black dots are those from about 1980 all the way through the year 2000. And what you can see on the kind of the left side of it, where you're in the range of, say, 100 to 200,000 cubic feet per second, is that the data sets don't look particularly different. There's not a really substantial difference in the amounts of phosphorus coming out. But as you begin to move up, and especially as you get up over about 400,000 cubic feet per second, you see a real separation, with the red dots being, in many cases, substantially higher than the black dots. All of this suggesting that there really is a change in the way the system is responding to high flow events. And in fact, the highest flow event took place prior to 2000. The highest monitored event took place before 2000, and it had a concentration well below 0.5 milligrams per liter. So it certainly suggests that conditions have changed over time. In this case, I'm using a model called WRTDS, weighted regressions on time, discharge, and season. And for those interested, I've mentioned at the bottom of the screen a web address where you can get more information about this model and the R package that's now available. It contains a variety of tools that help us look at these kinds of descriptions of change. And this is just one example of a way to look at this situation. The two curves on here are smoothed estimates, and if you're familiar with low S, this is a kind of low S process that's going on, and we're simply seeing the red one is a curve centered around data from around 2005 in the autumn part of the year, and the one in black is from 1990, centered around 1990. And what they show is that it discharges below about 100,000 cubic feet per second. The patterns are quite similar, but as we move above 100,000, they begin to diverge and diverge to a very great extent. And the graph that you see at the top is a contour plot, which is a representation of the expected value of concentration for any given combination of discharge and year. And what you see in this, and this runs from 1985 through 2011, and what you see is a pattern with a lot of seasonality to it, and what you see is the higher concentrations happening at the highest discharges, and that they begin to become more and more prominent as we move later and later in this record. And that's a reflection of the same thing that we really saw in the previous graph. We're taking sort of one slice of time, or two different slices of time through this same graphic. And the reason what's going on, the kind of change that's happening, and this is a picture of what's happening at the dam, and the monitoring point is at the dam, is that the reservoir is basically been in place for about 80 years. It's rapidly filling with sediment, and the trap efficiency is declining, so that at any given flow, we have a lot more throughput from this system than we did in the past. We're going to show two examples here of what this particular contour plot looks like, one around 1994 and another one around 2010. And these are just the same contour plot, but just blown up so that you can see it better. So again, time is on the x-axis, discharge on a log scale is on the y-axis, running up to 200,000 cubic feet per second. And what you see is that the lower discharges, these pictures are really quite similar between the mid-90s and around 2010. But at the higher discharges, they're vastly different, with much higher concentrations being seen in recent times than were seen before. And this, again, is just an example of a interpretive tool that helps us try to really make some order out of what is otherwise rather chaotic-looking data. We can analyze it, and I won't go through the whole process by which the analysis is done, but this is really the outcome. And the green line on the top graph represents what's called the flow normalized concentration, annual concentration as we move through time. And what you see is that those concentrations were coming down to about 1995, and since 95, they've been fairly level to slightly upwards. The dots indicate the individual year values, and they vary a great deal because of year-to-year variation in discharge, but the underlying change after we integrate out the effect of flow variation is a very slight upwards trend of about 0.4% per year averaged over that period, 95 to 2012. The bottom graph, using the same analytical process, computes a flow normalized flux, and that's seen as the green curve. Now, it's displaced very much toward the bottom of the graph because one of the individual annual values is so high, and that's the 2011 value, which is associated with Tropical Storm Lee. But the slope on that curve is much, much greater than the slope on the concentration curve. This one is 3.1% per year. My point here being is that we have a big change at high flows and almost no change at low flows, and as a consequence, we have a large trend in flux but not a particularly large trend in concentration. If your objective is the cleaning up of Chesapeake Bay and you want to limit phosphorus inputs, the thing to be focused on is the flux story and not necessarily the concentration story. So the hypothesis about what's actually going on in this system is that as the reservoir fills, for any given discharge, there's less cross-sectional area resulting in greater velocity. This results in a decrease in the scour threshold, or more frequent scour events, and greater amount of scour for a given discharge. Also, a decrease in the amount of deposition at moderately high discharges. And for most of the last 80 years, the output has been less than the input, but ultimately the output of this system must equal the average input, averaged over a period of years, because it's at some point, and we're almost at that point today, that we're reaching that capacity. And unless there's a dramatic decrease in the inputs, the outputs of particulate nitrogen and phosphorus and of suspended sediment must rise either naturally or by engineered removal. And this is a topic of great controversy and discussion, including people talking about in the recent gubernatorial election as to what to do about this situation. And I'm not going to comment on that, but my point I wanted to make here is that the analysis of the data, and particularly the high flow event data, is critical to trying to understand how this system is evolving. And I want to encourage people to collect the data, and also to analyze it, to understand how today's high flow events might compare to what might have happened in similar high flow events in the past. I'm going to move to my next sort of topic, and that's high flows after droughts. And Iowa has been the poster child for this situation recently. I'll quickly show you an example from the Iowa River. This is published in a paper by Jennifer Murphy, myself, and Laurie Sprague in the journal Hess in 2014 on antecedent flow conditions and nitrate concentrations in the Mississippi River Basin. And we're looking here at high flows right after a drought. And in this paper, we defined a couple of terms. We defined something called a flow anomaly, which is the ratio of the average discharge over the past 365 days as compared to the long-term average discharge. So that after a major drought, the flow anomaly would be some number less than 1, versus after a high flow year, the flow anomaly would be greater. It's a number which simply represents sort of an integrated view of the most recent year's worth of data, and the flow anomaly can be computed at every single day as we move forward in time. We also compute something we call a nitrate anomaly, which is the nitrate concentration residual from this WRTDS model expressed in natural log units. So the WRTDS model says on a particular day and at a particular discharge, not considering this memory process of what's happened to discharge, we can estimate what nitrate should have been, then we compare with the nitrate that we actually got, and the anomaly is the ratio of what we got to what we estimated without knowing something about this history. And what we found in this study at a variety of sites, the Iowa River being one of them, is that there's a significant negative relationship between the flow anomaly and nitrate anomaly. And here's an example graphic from that paper. So the flow anomaly, so to the left on the x-axis, would be situations where we're in or have just come out of a drought, and to the right are situations where we're in or have just recently experienced a high flow condition. And the nitrate anomaly, and I put to the right an expression of the nitrate value as a percent of the median estimate, where the median estimate was one that's done without relationship to the previous flow conditions. And what we see here is at the top of the graph would be the observed would be about 270% of what we would expect, and at the bottom it would be about 37%. So in the particular case, and we did this before the very severe drought of 2013, but I'll show you an example from that in a moment, drought of 2012 in this area, we would be way to the left on that graph, which would indicate that nitrate would be higher than it would otherwise be for a particular sort of a flow condition. And of course, the reason for that is that we have a buildup of nitrate in the soil. The plant uptake processes, the leaching processes, the denitrification processes and other biological processes that might take place in the stream or the hyporeic zone are very much suppressed during a very dry year, so that when we start getting wet conditions at the end of that dry year, we're likely to see much higher concentrations than we would have if conditions had been more nearly average over time. So it's an important consideration in understanding what's happening in water quality. Now, this is another site also in Iowa, and this is sort of telling the story of what happened in the aftermath of the very severe 2012 drought that really ended about the winter of 2013. This is a trace of nitrate concentrations in the stream as measured by an optical nitrate sensor that located in the stream, and virtually every 15 minutes for that entire period of time. And what you see is that coming out of the drought and coming into the springtime period, we had concentrations in the range of, say, 2 to 5 milligrams per liter. And as soon as things started to wet up, concentrations rose dramatically up to about 20 milligrams per liter here on the Raccoon River, which is near the site of the Des Moines waterworks. And then finally, as we move into the late summer, into the fall, concentrations finally come back down. And there's some very interesting kind of spiky behaviors. And every one of those downward spikes that you see in there, it represents a time when stream flow really came up significantly at that time. And here, in fact, is the discharge record that was occurring over that exact same period of time that you saw, and it's on a log scale. So you see discharges going from 1,000 on up to over 20,000 cubic feet per second in the aftermath of the severe drought. Now, another way of looking at that same information is to plot concentration here on the vertical axis and discharge on a log scale on the horizontal axis. And it's a very complicated picture, but you start the beginning of that record, the beginning of April, over where the word start appears, and we move across the page and then up, and then finally ending up on the far right-hand upper edge, and a very interesting sort of behavior showing that, in fact, as discharges rise, concentration stayed the same. Then when discharge stopped rising, concentrations came up, and that happened in 2 or 3 episodes, forming some of these loops, hysteresis loops that we see here, and then a lot more complicated behavior. We've never really had data sets like this until very recently, and I would argue that this is a really fertile ground for research and understanding of how systems behave. But I want to show you here is I'm going to superimpose on here the same kind of record for April, May, and June of 2014, and now I've superimposed that. So the black squiggles are the 2014 data, the red ones are the 2013 data. And what's particularly interesting is that 2014, the discharges rose to nearly the same levels that they did in 2013. They got up well above 10,000 and almost to 20,000 cubic feet per second in 2014, but the concentrations never rose above about 10 or 11 milligrams per liter in 2014, whereas in similarly high flow events in 2013, they rose up around 21 milligrams per liter. So the particulars of this high flow event in 2013, following on the heels of the preceding drought, was really a special case. And we need, well, let me just go on to some of my general comments about it. So concentrations in the aftermath of a drought can be very high, and a simple concentration versus discharge relationship that just simply looks at the current discharge will not capture this kind of phenomena. Unusual conditions right after a flood or a drought may not be indicative of long-term trends. What we saw there was in 2013 extremely high concentrations, but in 2014 at similar discharges it came back down. So it was really an aftermath effect as opposed to a real change in the system. Understanding the process is far more complex than anything we can ever learn from monthly or even weekly data. But sparse data is often what we have, and we need to look for changes over all seasons and flow conditions and through multiple floods and droughts if we're going to understand how these systems are behaving under these changing conditions. I just want to very briefly end with a couple thoughts about climate change and as it relates to water quality. One of the thoughts is a recognition that over the long haul, looking at many decades in any given stream, and I'll show you two quick examples, high flows are very much serially correlated. They tend to cluster in time, and demonstrating trends in high flow conditions can be extremely tricky, and that what we often see is more this persistence phenomena as opposed to a really underlying trend. The theoretical and empirical underpinnings of streamflow changes due to greenhouse forcing is, I would argue, very weak. And if you read the most recent reports from the IPCC or the National Climate Assessment, they basically are coming around to this conclusion that the evidence continues to be very weak, and that, in my view, blaming water quality issues on climate change is a cop-out. The fundamental reasons of water quality problems tend to be things that we're doing at point sources and non-point sources on the landscape, and that what we're seeing in terms of intense events and flow may possibly have something to do with climate change, but the real drivers are what we're doing in the watershed. This is just one way to look at a discharge record. This is the Susquehanna, the example that I showed at the beginning, where some people said, well, maybe we're seeing all this stuff coming out because we're getting more floods or they're more frequent. This is actually the hydrograph of the Susquehanna River, but it's been truncated here at 200,000 cubic feet per second. So our focus can be entirely on what's happening above that threshold. And what you see is clumps of years with many or a few years that have many high flows, and then other long periods of time without any, and discerning any kind of a real underlying trend is very difficult. The Iowa River, which I talked about before, here's the record going all the way back to 1914, all the way up to present. And again, very clumpy behavior of these high flow phenomena. And just looking at a few years and saying, oh my God, high flows are getting a lot bigger and a lot more prevalent, I think we have to take it with a grain of salt, and we have to look at it over these very long periods of time. I'm not saying that these things won't change in the future as greenhouse gas increases, and I want to be on record saying I'm not a climate change denier by any means, but this linkage to streamflow conditions remains very, very murky, both on a theoretical and empirical basis. So my main points, just to kind of repeat and then wrap up, samples during floods are critical to estimating fluxes, and continuous monitoring can be extremely helpful for that. Trends in average concentration and trends in average flux can tell very different stories. Low flow conditions as well as high flow conditions can have a lasting impact on water quality for as much as a year or more. And then greenhouse forcing impacts on extreme flows is very uncertain. And I finally just want to end with a little plug for the software that we've made available, both for retrieving data from many sources, including NWIS and the EPA, the USGS EPA portal, these tools for data retrieval and data analysis, and the website that describes them is at the bottom. Thank you for your attention.